The following program is brought to you by Caltech.
Good evening. My name is Tom Sofer. I'm the chairman of the Division of Physics, Math, and Astronomy here at Caltech. Before I introduce tonight's speaker, let me announce that our next lecture in the Watson Lecture Series will be on January 30th and will be given by Professor Tracy Dennison of the Division of of Humanities and Social Sciences, not Physics. Her title is For Love or Money, Marriage and Economic Development in the Past. So tonight, it's my great pleasure to introduce our speaker, Harvey Newman, who is a professor of physics. Harvey received his undergraduate and graduate degrees from that technical school in Cambridge, Mass., whose most illustrious graduates are Click and Clack of Car Talk fame. Harvey's been a member of the Caltech faculty since 1982. Harvey does big science, indeed the biggest science. He works in high-energy physics, and he began his career as a co-leader of the Mark J collaboration that discovered the gluon at the DESI laboratory in 1979. Harvey's been a member of the Compact Muon Solenoid, or CMS, collaboration at the Large Hadron Collider, or LHC. You have to learn the acronyms, since 1994. And he worked on the experiment for the US version of this experiment, the SSC, for 6 years before that. So in total, he's worked on this experiment for 25 years, roughly half a scientific career. The LHC and its two main experiments, CMS and ATLAS, have been described as the most expensive and most complex scientific project ever undertaken. All of this effort paid off handsomely last year with the announcement on July 4th of the discovery of the Higgs boson. To quote Science magazine, "For all the hype, the discovery of the Higgs boson easily merits recognition as the breakthrough of the year." Harvey and his team, including his colleague, Professor Maria Spyropoulou, have played a central role in this great discovery. In addition to his spectacular work in physics, Harvey's been a great mentor to Caltech students. Besides guiding a large number of graduate students, he and Maria have mentored more than 90 undergraduate SURF projects. Clearly, he's had a great influence on undergraduate education at Caltech. Harvey's been a great leader in high-energy physics over the years, having chaired the U.S. Collaborative Board for CMS for over a decade, and he now serves as the chairman of the U.S. LHC Users Organization. As a leader in major international projects, Harvey is well-traveled. He's crossed the Atlantic more than 700 times. And I'm sure that besides his family, he's loved by many airlines. Harvey's a fellow of the American Physical Society and has received honorary degrees from universities in Romania, Slovakia, and Brazil. Tonight, Harvey will share with us the excitement of discovery in his talk, Physics at the Large Hadron Collider. After his talk, he will take informal questions up here at the podium. Now, let me introduce our speaker, Harvey Newman.
Thank you, Tom. It's a great honor for me to be here with you tonight, 3 years after my last Watson lecture, to take you through the journey that we've all shared coming up to the discovery of a new particle called the boson, which may be the Higgs boson, thought to create the mass of fundamental particles in the universe. To show you that the milestones along that road, and most importantly, to show you a preview of what may lie beyond, because it's the quest for new knowledge which is the true purpose of our science and our work. So in the course of this lecture, I'll take you through a brief review of the half-century search, starting with the theoretical framework, the LHC and our experiment, CMS, the process of discovery, and then what may lie beyond the standard model in the future. You can see here views of the detector, the apparatus to measure the particles, the LHC, some of the key events which you'll come to understand in the course of this lecture, and this view of collisions of the very intense environment that we live in and that we have to overcome to do this science. So particle physics is that field which addresses the most fundamental questions on the nature of matter and space-time. What are the most basic constituents of matter and the forces, the interaction between them at the most basic level? What is the origin and composition of the universe and how did it evolve? And are those constituents that we see today the same and also the same physics as we saw as we had in the early universe? It's these questions and these types of questions that have inspired some of the best and brightest students around the world, including many at Caltech. And as Tom mentioned, it's been a great privilege to mentor not only graduate students, but many extremely talented undergraduates, many of whom are now senior members of our physics community. These are the real heroes of the discovery. These are the members of our group. There are many students, graduate students, young staff, postdoctoral fellows, and I'd like to highlight here at the bottom some of our most recent undergraduates who worked at CERN this summer and participated in this exciting discovery. This is that milestone on July 4th, 2012. It was at midnight, California time, when the discovery was announced, both by our experiment, by CMS, and by Atlas. And you see 5 of the 6 directors that contributed to this project, including the present director at the time of announcing this discovery. This was the culmination of nearly a 50-year process. The theory first formulated starting in the 60s, the LHC and experiments conceptualized in the 1980s, the beginning of construction of 2001, and finally the operation in 2009. When I stood here last time, 3 years ago, we had a very exciting startup, followed by a very exciting accident. And after a 2-year interval, the machine restarted and the experiment started magnificently. I already talked about the beginning of that last time. And here we are at this major milestone, not only of science, but of humanity. And you can see the impact in many countries, both in Europe and also in other regions of the world at the time of that milestone. This is about the startup in 2008. 1 billion people watched. You can see here Google showed the collisions in their own way. And it was September 10, 2008. The accident occurred 9 days later. Nevertheless, after the restart, now we've had this magnificent 3-year run, and 2012 especially has been a banner year. So the Standard Model is a 50-year edifice of physics, which is a beautifully simple picture of the most basic constituents of matter, how they interact, and how matter in our universe is constructed. There are 3 families of quarks which participate in the strong interaction, which is the interaction that binds nuclei together. And the first generation of these, the up and down quarks, are what compose the protons and neutrons in the nucleus, normal matter. Similarly, there are leptons, and the first generation of that includes the electron, so that here we can complete atoms with the first generation. The other generations have been discovered in cosmic rays, the muon, and also at previous generations of accelerators. Starting in the 1960s for strangeness in the second generation, then other quarks progressing actually in mass as you go from generation to generation in more recent discoveries, culminating with the top quark at Fermilab in 1995. There's also a third generation of leptons, a heavy lepton, called the tau particle, discovered in 1975. And there are 4 carriers of these forces, describing 3 of the fundamental forces of nature: the electromagnetic, the weak, and the strong interactions. Electromagnetism carried by the photon, the strong interaction carried by a set of gluons, and the weak interaction carried by 2 heavy particles, the Z boson, which has no electric charge, and the W boson, which does have electric charge. There are a number of shortcomings of this beautiful, simple theory. It does not incorporate gravity. It doesn't describe in any way what explains dark matter, which we know exists in the universe. It doesn't tell us other things, such as the pattern of particle masses, whether the forces of nature were unified in the early universe, why there's a predominance of matter over antimatter in the universe we observe, and this, and indeed nothing in particle physics yet, tells us much about dark energy. So this is a beautiful, simple picture, but it leaves so many questions unanswered. The theoretical structures that we use, that are the foundations of the Standard Model, started with field theories, the first of which was invented by Richard Feynman, following 12 years of struggle after wrong advice from his advisor at Princeton. This was overcome in 1947. A fantastic quantum theory of electromagnetism with extremely powerful predictive capability. The second is a unified theory, which I'll describe how it came about, of electromagnetism and the weak interaction. That's the one that describes radioactivity, put together by these 3 gentlemen after a long process I will describe: Glashow, Weinberg, and Salam. The third fundamental theory that makes up the Standard Model was invented, including by one of the faculty here at Caltech, David Politzer, quantum chromodynamics. And one of the key elements is that quarks, which carry the strong interaction at very high energies, have the same kind of interaction. Their interactions become weaker so that one can treat them in the same way as the other interactions. And of course, a key element, the one that describes how mass comes about, is the Higgs boson. This is just a little bit about that third theory, which I had something to do about experimentally. David Politzer got the Nobel Prize for this phenomenon called asymptotic freedom, this fact that the forces become weaker at high energies or shorter distances among the quarks. So I participated, as Tom mentioned, in the discovery of gluon jets in Hamburg in 1979. And also we could see here in another one of my previous experiments, a 3-jet event in the Large Electron-Positron Collider, which occupied that same 27-kilometer tunnel that the Large Hadron Collider now occupies. In fact, this picture was made by my first graduate student at Caltech. Even then, we were searching for the Higgs boson. What about the Higgs boson? The theoretical framework starts with an idea called spontaneous symmetry breaking. This is an idea that we see in many places in nature. The fundamental theory has some symmetry, but the states we see don't have that symmetry. We see that in magnetism, where there's a preferred direction, where the magnetization goes in a certain direction, but there's no preferred direction in the theory. We see it in ice crystals freezing on a window pane, taking first certain directions. We see it in the structure of snowflakes. But what about a fundamental quantum theory? A physicist named Nambu, who won the Nobel Prize in 2008, first proposed that spontaneous symmetry breaking could be the source of massive particles. His advisee, Goldstone, studied these theories, but found instead that when you break the symmetry, you produce massless particles. That created two problems. One, no explanation for mass. Two, there are all these massless particles which are not seen in nature. Phil Anderson, another physicist in 1963, showed how under certain conditions, when you break the symmetry locally in different ways at every point in space, you can go from massless to massive states in superconductors. Then Peter Higgs, being inspired by this and other earlier work, and others at the same time, showed how to transform away these massless particles that don't occur in nature and to keep the massive ones. And in particular, those three gentlemen, Weinberg and Salam, building on the work of Glashow, showed how to put it all together, how to unify electromagnetism and the weak interaction, how to transform the theory so those massless particles are somehow eaten, like this, giving rise to the massive W and Z bosons. The photon remains massless, which is good, that's what we have in nature, and suddenly there appears the Higgs boson. The Higgs field is a very special field. It doesn't emanate from any other source. It fills the universe. And it is through the interaction with that field of particles that travel through the field that mass is acquired, in particular for those basic constituents of matter, the quarks and the leptons. So imagine that you have a room full of physicists, like analogous to the Higgs field. They're chattering quietly throughout the universe, and suddenly a famous physicist, like a particle, comes into the room, and they all turn towards him, and they all cluster about him. And so, having clustered about him, he finds it much more difficult to move around. And so that's just like the process of acquiring mass. In other words, just like a particle acquiring mass as it moves through the Higgs field. Okay, so now let's turn to particle physics experiments. What do we need? Accelerators. Very powerful accelerators to accelerate the particles. The LHC accelerates protons to very high energy and to bring them into collision. Detectors such as CMS and our competitor Atlas, gigantic instruments, ensembles of instrumentation that record the particles and measure their properties such as their momenta and direction as they stream out from the collision points. Computing grids. It takes a worldwide ensemble of computing facilities and networks to store, distribute, and enable physicists to analyze the vast amount of data, which actually amounts to many millions of gigabytes of data per year produced by the detectors. And above all, it takes people. Only a worldwide collaboration of scientists, engineers, technicians, and support staff, very talented people, can design, develop, build, and operate such a complex instrument. So we start with accelerators. Accelerators do two things for us. First of all, of course, to provide sufficient energy so that we can create new particles on an energy scale and equivalently on a mass scale that hasn't been touched before. And also to probe down to small distances, to examine the forces of nature on small distance scales which haven't been accessible. And so by going to high energy and high momenta, we effectively also give ourselves resolving power we didn't have before. And the energy scales we reach can be thought in the cosmos in terms of equivalent temperature, and therefore there's a connection with what happened in the early universe. And so accelerators like the LHC recreate particles that were rarely seen in nature since the first moments after the universe was created. And what we can see here on the left is actually a sequence of, as you go up in energy, you can probe from atomic scales to the nuclear scale, to the nucleon scale, and then to the constituents of the nucleons, and further. Before the LHC, previous accelerators at CERN, at Fermilab, and Stanford provided the foundation for the exploration which we're talking about tonight. They established this unified electroweak theory and the standard model, also of the strong interaction. They showed the existence of the W and Z particles, measured their masses very precisely, their properties, many of their properties precisely measured to 1 part in 1,000, and also searched for new particles. And what you see here in one graph is 12 years of data from the previous accelerator, the Large Electron-Positron Collider, which first studied the Z particle. This is a logarithmic scale, so you see an enhancement by several orders of magnitude, studying the Z particle. Then going to higher energies beyond the Z particle, eventually you could produce pairs of W particles, pairs of Z particles, and all the while searching for the Higgs. And down here at the bottom, there was a projection of what could have been a few events had they been there from the Higgs. And in fact, there was such an indication, which turned out, after a struggle and measurements, to be a statistical fluctuation. Enter the LHC. This is a view of the topography of Switzerland and France. The accelerator crosses the border. Here, as Tom mentioned, this is a very important element. This is the airport to get there. Actually, the accelerator is 150 to 500 feet or 50 to 150 meters below the ground. The two major experiments are CMS and Atlas, and I'll talk mainly about CMS. And in fact, you can also see, if you look carefully, that it's really the entire ensemble of accelerators at CERN which accelerates the protons starting from a hydrogen bottle, and then through the earlier generations of accelerators, and finally the LHC, brings the protons to 4 TeV per beam this year, and 8 TeV in the center of mass. Why the LHC? Why is it the right machine? We've known since the 1980s, with the standard model, that something has to happen by the time you reach the tera-electron-volt scale, the energy scale equivalent to roughly 1,000 times the mass of a proton. Either the electroweak theory would essentially become strong and fall apart, or something would have to exist. Could be the Higgs boson, could be something else. And we didn't know particularly what the mass of the Higgs boson would be. Could be as much as close to 1 TeV itself. So several TeV of proton energy is needed so that the constituents of the protons, which are actually the things which collide, the quarks and energies of the LHC, actually the gluons which hold the quarks together, are those things which most collide that we study. You can see two sequences of hadron colliders, that's proton-proton and proton-antiproton colliders, and electron-positron colliders, which are complementary. These have a cleaner state. The electrons and positron annihilate. There are no fragments left over. All the energy goes into producing possibly new things. But the energy is lower because electrons are light, and they radiate a lot. And it takes a lot of electrical power to make up for that radiation. Hadron colliders can go further. And the LHC in particular, a proton-proton machine, is the first to go well into the TeV scale. In searching for new things, we have to be able to examine lots of possible different energy scales at once. And so we'd like to do what we call broadband scanning. The protons contain quarks and gluons of many momenta. And therefore, when we collide protons, we're creating these different states of energy all at once. So a proton-proton collider with the highest energy and the highest luminosity, which you can think of as intensity, is the right machine. This is a graph that illustrates the difference between the LHC and the previous generation. The Tevatron took us up to a parton-parton center of mass energy. This is on a log scale, many orders of magnitude, cutting off at about 1 tera-electron volt, and the LHC going well beyond. And in particular, you see the gluon-gluon collisions and also the quark collisions which the LHC creates. So the LHC is a discovery machine. It takes us deep into the TeV scale, the tera-electron volt scale. And there are many reasons to expect new physics. We found a particle that looks like the Higgs, but we don't know what lies beyond. And we know that the standard model for all its successes are incomplete. So the real search is for all these exotic possible things of nature. And after all, science is about discovering new things, and we do not know ultimately what we will find. So this is about the LHC. I've said some of this. There are actually two rings where bunches of protons circulate in opposite directions. There's a bunch every 50 nanoseconds. They're very intense. There are, as shown here, of order 100 billion protons in each bunch. And you can compare these two columns. This is an early cartoon of design values, and this is what has actually been achieved this year. You'll notice the energy is less because after the accident, we couldn't operate yet at full energy. After we have this repairs going on starting this spring, we hope to go at or close to the full energy. But we already reached, with half of the proton bunches, close to the design intensity. And in many ways, this is a really superb instrument. Its acceptance, its ability to accept protons, its focusing power, the quality of the beams, thinking as an analog of an optical system, how well you can focus it with a very small spread in position momentum space, are actually better than the design. And so this combines high energy and very high intensity. And it's that combination that allows us to search for and to find rare processes. And also, in the milestone discovery of the Higgs-like particle, as you'll see, we're dealing sometimes with one event, one collision in 100 trillion to find the key signals. This is the progress of the LHC in what's called integrated luminosity. The units are inverse femtobarns. What does it mean? An inverse femtobarn means we created about 70 trillion collisions. And so what the LHC has done up to the time of the discovery in July, we had 5 inverse femtobarns in 2011 and about 6 delivered in 2012 at the time of the announcement. And after that, the LHC went on and has since delivered quite a bit more luminosity. Overall, compared to the discovery, we roughly have 3 times the data, including the 2011 data, that we had at that time. And also the progress has been phenomenal. So after the accident and recovery, which I already talked about, we had a startup with some luminosity in 2010. To see anything on this scale, we had to blow it up by a factor of 100. Then the next year we have this curve, which is the 7 TeV data, and now the 8 TeV data. So a phenomenal rate of progress. Overall, in 2012, in common terms, we created 2 quadrillion proton-proton collisions. So that's 2 times 10 to the 15 in scientific notation, proton-proton collisions on the path to discovery. What about detectors? Detectors are a complex, perhaps the most complex ensemble of instrumentation ever devised by mankind in this program. Around the collision point, you put specialized detectors, each of which is designed to detect and measure a certain type of particle. Photons, electrons, muons, jets of particles which are the product of quarks. Quarks cannot actually appear bare in nature. The other part of that theory, quantum chromodynamics, which I mentioned, is as the quarks and antiquarks fly apart, they pull other particles from the vacuum, and you see jets of particles. Neutrinos escape and are seen indirectly as missing energy. When you add up everything that you see, you should have conservation of energy momentum, so a total momentum of 0, and an energy, certain energy. And if there's an imbalance, then it's a sign of neutrinos or possibly other very weakly interacting particles which escape the detector. So here's CMS. Here's a perspective view. And here's a sector cut out so we can see how it works. And if this works, we'll be able to see a bit more. So here's how the different parts are used. Muons travel all the way through. Inside, you have this tracking detector with 200 square meters of silicon. Crystals, which measure electron and photon energies. Muons go through, and they're also measured outside. The electron has a track in the tracker, and most of the energy goes into these crystals, 76,000 crystals. A neutral hadron leaves no track, and then most of its energy goes in this additional layer called the hadron calorimeter. A charged hadron has a track, and again, most of its energy in the hadron calorimeter. And a photon, no electric charge, so no track, and then its energy in the crystals. This is a time-lapse view of the construction of CMS. It's a radical design, highly modular, where the major components, there you see my colleague, Maria Sparopoulou, during the construction. The major components are first assembled and instrumented on the surface and tested and then lowered down. You see some of the major elements. This is the heaviest element, weighing 2,000 tons, that was lowered in February 2007. It took 11 hours to go the 150 meters, the 500 feet to the ground. This is the superconducting solenoidal coil that generates a magnetic field of 40 kilogauss. And finally, the detector has landed. So the compact muon solenoid, compact means dense, it doesn't mean small. 12,500 tons, contained in a volume 21 meters long, 15 meters in diameter. The stored energy in the magnet is 2.7 gigajoules. What does that mean? This is the amount of energy it would take to raise 28 tons from sea level to the top of Mount Everest. It's also the kinetic energy of the largest man-made moving device, like this aircraft carrier, moving at 20 miles an hour, 117,000 tons. That magnetic field is what drives the measurements of momentum of the particles, charged particles, which I showed earlier. So here's CMS buttoned up. It has some exceptional subsystems, like a silicon tracking system with 200 square meters of silicon. It's an enormous amount of silicon. Heavy crystals weighing 90 tons, which provide precise measurements of electrons and photons. And it works beautifully. It works beautifully in that it has operated at 94% efficiency, meaning that we collected about that much of the amount of data delivered by the LHC. And it works beautifully in that the number of channels working in every one of the subsystems is close to 100%. Some of the things that Caltech has done which are special. The heavy crystal scintillators, which I use to measure electrons and photons, were developed to a large extent in our crystal laboratory, which was established first for studies for the SSC in 1983, and it has studied crystals for several generations of experiments. As the experiments progressed, you can see that the crystals get smaller because they get more dense. Higher energy measurements, we need to contain more energy in a short space, and we chose and also helped develop new scintillators such as this one, which we use in CMS called lead tungstate, whose density is greater than that of iron, but of course it's very clear. And the light created in the crystals can propagate to the photodetectors and be converted to electrical signals, and we can read out the result precisely where the amount of light and therefore the amplitude of the signal gives us the energy of electrons and photons. You also see on the right, I'll talk a little bit towards the end about the next generation high luminosity LHC, a new crystal which is fast and bright and very radiation hard for the next generation of the LHC, perhaps a decade from now. We also created the computing model, the worldwide computing model, which I developed in 1999. You see a worldwide ensemble of computing facilities represented here. The data flows from the detector, is reconstructed into physics quantities for the first time at the CERN laboratory. It's then distributed among many national centers, of which there are now 11. We also invented the first Tier 2 center, the facilities that are used at universities and the smaller laboratories, of which there are now 160. The nature of this ensemble as a system depends upon networks. So we've attacked and now have the state-of-the-art in terms of understanding and operating such networks with the highest throughput. And the entire thing functions as a global dynamic system, particularly from the network point of view, where we operate and co-manage transatlantic networking for the field. This is one of these special systems, a global, intelligent, autonomous, real-time system that monitors tens of thousands of computers and many of the major links on research and education networks. Since the experiment started again, the physics output has been remarkable, starting from the early days. In 2010, with a small amount of data, which I showed you, we essentially went through the process of experimental discoveries, of old discoveries, not true discoveries, but rediscovering what was already known. And so this is a beautiful picture where on the top we show the original discoveries of particles from cosmic ray muons, the pion, the strange particles, the strange heavy particles called baryons, which were in Murray-Gell-Mann's eightfold way, the bound states of quarks, charm quark and antiquark, bottom quark and antiquark, the third generation, the Z particle and the top quark. This is a span, as you can see here, of about 50 years. And in CMS, recreating this, first cosmic rays on the surface, 2006. But then with the LHC, from December 2009, in the space of just less than 8 months till July of 2010, all of these discoveries recreated. So we knew that, we're on the right track. And of course, we looked and we're checking in a new energy regime whether there was anything that wasn't predicted by the standard model, and the answer was no. Okay, so what about the Higgs? As of July 1st, 2001, this was the only Higgs, Peter Higgs. But there was a process of search for decades, and so things narrowed down, both direct and indirect measurements, precise electroweak data at LEP, which I showed you, and we narrowed down the remaining range. And soon, by the end of last year, we only had a narrow 13 GeV gap left, a very narrow energy range left. And by December 2011, we had ruled out Higgs masses from 127 to 600 GeV, up near the limit where the standard model makes sense. How are Higgs particles produced? How do they decay? What do we look at? Well, the leading way in which a Higgs particle could be produced is two of the gluons, which are constituents of the protons, which are colliding, can come together and fuse. Now, the Higgs couples to mass. It cannot couple to gluons directly because they're massless. So there is in here this triangle, which can be other forms of matter. For example, a top quark in a loop, a heavy particle, which then leads to the production of the Higgs. That's the most copious way it's produced. But of course, it's hard to pick out these events, and there are other channels which are also useful. A quark and an antiquark in the proton, one each, can come together, and they can each radiate a W or a Z boson, and those together can form the Higgs. This is an even rarer process. It's an order of magnitude less, but you get these additional jets of particles from the leftover quark and antiquark, and that's a more distinctive signature, and therefore is useful because it has a higher signal-to-background ratio. In the massive number of possible background events, this is a topology, a signature, which can be picked out more distinctly. And there are other modes, like the one we used at LEP was called associated production, where you produce the Higgs in association with a W or a Z particle. And what do we look at? Well, once the Higgs, if it's produced, it's an evanescent particle. It has a very short life, and it then decays. And there are many modes we can look at. The Higgs can go to a pair of Z bosons, or two photons, turns out to be very important, or a pair of Ws. Taus are leptons with mass, and a bottom quark and a bottom antiquark. Remember, the Higgs couples to mass, so you'd think that the most copious modes, the ones which are most frequent, are the ones involving the heavier particles. But in fact, in terms of what we can see distinctly, we have to choose very particular subchannels. And so I wrote two of them here. The Higgs particle going through this loop to two photons, that's only 0.2%, a very small fraction of all the decays, but very useful because it's so distinct. And another one is the two Z particles, each goes to a pair of leptons, an electron and a positron, and a muon and an antimuon. Two of those pairs in combination. That's only 0.01%. And of course, there are other modes, and we use those too. And you'll see how it all comes together. This is a chart on the log scale of all the possible decays of the Higgs particle in the mass range at which we were focusing, also being liberal after all the space that had been ruled out, but still in this range. It's interesting that many decay modes can contribute. So this is a pie chart showing how the Higgs decays. Mostly to, for example, the bottom quarks, to the force carriers, a pair of W bosons, what we use most, the ZZ, but even a subchannel of that. Of these, only 3% for each Z goes to a pair of these leptons. And that's why we get this very small production rate, but very important. And also the pair of photons. Eventually, we're going to bring all this together. And that's really what contributed in a very clear way, as you'll see, to the discovery. So this is the first very distinct mode, a very beautiful event. You see two high-energy photons coming out. They're represented by these green bars that's representing the energy in the crystals. It's a very rare decay, as I said. The analysis has been optimized to emphasize those events which are most clearly identified, measured, the point at which they emerged, also reconstructed correctly with highest probability, so we get the mass of the two photons when put together and reconstructed into a mass correct. And a key point is the high resolution of 1% in the central part of this detector. This is a very important mode in the discovery, and here you can see one of our students, Yong, who recently did his thesis and defended his thesis on November 7th. There are some key instrumentation challenges which were met in order to make use of that very distinctive mode. Here at Caltech, we developed a set of laser systems which measure the transparency changes in all 76,000 crystals at once, so that As their response varies, and because of the radiation that they suffer in the LHC environment, the response varies. One can measure, in fact, every 40 minutes, the transparency changes in all the crystals. Then one can combine this with another calibration method, which was invented here at Caltech, and checked by our ability to reconstruct a well-defined process of the Z going to an E+E- pair, and we can check that we're succeeding in all the crystals in maintaining the high resolution. The laser systems which are developed and commissioned here are stable to 0.1%, enabling us to maintain the 1% and, in some cases, better resolution. Another key technique was to be able to calibrate using physics. With so many crystals, you need a very high-rate process. And so from the first moments of running, we chose and developed a technique of using this light particle, the pi0, which decays to 2 photons. It only has a mass of 135 MeV, a seventh of a GeV. And yet we developed a technique to use this precisely. There was a special high-rate data stream. We eventually started taking several thousand counts per second of just this process of picking out these particles. And that allowed us to maintain the calibration. And eventually this contributed to the discovery in both of those modes, because we're getting high resolution for photons, and also with the crystals, it contributes to very high resolution for electrons and positrons. What you can see here, this is actually also the first physics occurrence when we first had collisions of the LHC at the injection energy of 0.9 TeV at the end of 2009, and also on that wonderful day when the LHC started operation at 7 TeV. Here, the New York Times actually visited us in Pasadena rather than going to CERN. And this is a celebration of the first collisions. And within 20 minutes of those collisions, the first physics output, the resonance of the pi0, which started us on the path to precise calibration, and to that part of the Higgs discovery. In the midst of all of this, and with the increasing power of the LHC, there's a great technological challenge, the challenge of pileup. Every time the bunches of protons cross, every 50 nanoseconds, and starting when we restart, it will be every 25 nanoseconds. In other words, every 50 nanoseconds means 20 megahertz. Every time there's a crossing, there are an average of 20 interactions and up to 50. And here's a spectacular event with many particle tracks coming out. You're looking at a very small scale along the beamline and seeing many vertices, 50 interactions visible, 14 jets of particles, 2 TeV coming into the detector. And yet the high resolution was maintained. From the calibration, from the corrections, and also for correcting from all the additional energy in the analysis that comes from these extra interactions. Next is a special class of events where there are 2 photons and these 2 jets. The rarer process, which I mentioned, where the 2 W bosons or the Z come together to form the Higgs, leaving over an initial, from the initial state, the quark and antiquark which form jets of particles. Even rarer, but more distinct. By July, actually by June, before it was public, we clearly had enough data to see something. In the actual analysis, we used machine learning to optimize the signal to background discrimination. We also use mathematical techniques called likelihood fits. But to visualize, this is a very elegant technique just to see what's going on. See here, this is the mass distribution for photon pairs. You see a smoothly falling background. You can produce real photon pairs and have photons that you can, fake photons you can fuse with particles from jets. And you could see an enhancement, to start to see the enhancement. This is weighted in such a way, sort of like our mathematical technique, just an illustration. This is the unweighted. Many people over the years in my group have contributed to this channel and its role in the discovery. I show here, try to emphasize the students at the top, including like Yong, who just graduated in this channel. Yossi actually worked on another new physics search channel you'll see in a moment, but he was the first to use some of these machine learning techniques that optimize the signal to background. And there are other students involved now. Alex here has a new technique, event by event, that will really improve this analysis. Many students are named here, and also many undergraduates, some of which have gone on. We seem to be populating with some of these undergraduates, Harvard and Princeton in particular. What are the keys? Precise calibration, optimized identification of photon in the presence of background, precise energy scale, and innovative analysis, and persistent. Well, the first thing you do when you're looking for such a thing is expecting nothing, you try to set limits. With enough data, this is the level for setting limits, which corresponds to the standard model backgrounds with no signal. We actually went below that. We calculated our sensitivity down here over this whole mass range. And this is what we observed. And there was an excess. This is not a bump as such. It's that we weren't able to set a limit as we expected. And there was an excess in this region around 125 GeV, and it was seen both in the 2011 data and the 2012 data. What do scientists do with this? How do we know if it's significant or not? What are the odds? What are the odds in particular that what we're seeing is something significant and not an upward fluctuation of just the backgrounds, the normal processes without the Higgs? And so we compute these probabilities, and I'll try to describe this to you. So be patient. Across this mass range, this is what we saw. The probability of background only, and when suddenly we saw this dips. The 2011 data is 7 TeV, shown here. The 8 TeV data shown here, and together. The probabilities are down here. They're very small values. What do they mean? What it says is down here, there's just a chance a bit above 1 in 100,000 that it's background only. And so we convert these numbers in what are called sigmas. And this was also in the press. It's the number of standard deviations away from the expectation for a normal distribution. If you're 1 standard deviation off, 1 sigma, that happens in one direction. 1 in 6 times, that happens pretty often. By the time you have 3 standard deviations at 1 in 740. By convention, the scientists have come to call this evidence, but not yet sufficient grounds for discovery. 5 standard deviations, 1 in 3.5 million, is called an observation, also known in common language as a discovery. In this one channel, this excess had a significance of 4.1 sigma, so strong evidence, not yet a discovery. The next channel, very distinctive, called the golden mode, because it's so distinctive, because the signal to background after selection is quite relatively high. And here are 2 beautiful events, one in which one Z goes to an electron and a positron, and the other Z goes to a muon anti-muon. And you can see the 2 muons and the electron and positron in this event. So electron and positron and the 2 muons. And over here, another beautiful event involving 2 electron-positron pairs. There are rare events. You see 2 pairs of leptons coming from a common vertex, a common origination point. You can measure the mass to 1 to 2%. What you observe is a narrow mass peak over a smooth background. And so here's some of the results. With enough data, remember, we created 2 quadrillion proton-proton collisions in 2012. This is both the 2011 and 2012 data. And in this region near 126 GeV, we see this enhancement. There are 13 events in that enhancement. We observe overall in that range 17 events. The expected signal is 12.5. The expected background is 6.5. Signal to background 2 to 1. The signal events are 1 in 100 trillion. How do we know we got the mass right? Well, we calibrate also muons and electrons, but here's a beautiful result. There's a higher order process where a single Z can go to 4 leptons. You have a decay to a lepton pair, then one radiates a photon. It's called a virtual photon, and then it creates another lepton pair. And we can measure the Z mass, which is known very precisely. It's a known mass. It was measured at LEP to 2 parts in 10 to the 5th, 2 parts in 100,000, and we can see it's in the right place. So that's like an internal standard telling us we have the mass right, and also the rate is predicted, and we see things at the right rate. So we can use this result to test, is it the standard model? And remember, I'll show you various aspects, but they're only the first elements of a decision. In this channel too, there's a significant excess of our background, 4.5 sigma at about 126 GeV. The signal strength is 0.8 with these errors, so it's compatible with the standard model, which in the way this is normalized would be 1, so it's compatible. And the mass is rather precisely determined. If we combine the 2 channels with precise mass determinations, we get this very nice measurement of the mass of this particle. And over here you see this pretty picture of the best fit in terms of the mass here, the signal strength, which is not much below the standard model strength. And the dark colors are the best fit regions, and then you go out 1 standard deviation and 2 standard deviations around that best fit point. As I said, and I will spare you some of the details, there is a grand combination. There are many other channels, which for the interest of time I'm skipping. They all contribute. These high-resolution channels are the most important, with 4.4 sigma and 4 sigma significance. There are also, we see indications in the W, the decay to a W pair, to 2 heavy quarks, bottom anti-bottom quarks, and the 2 tau leptons. And all of them fall short individually of this 5 sigma criterion for discovery, but together there's a 6.9 sigma significance. The signal strength combined is 88% plus minus 21% of what we predict from the standard model, compatible with the standard model. But the odds against the background fluctuation only are 1 trillion to 1. How compatible is this result with the standard model? We can look at the individual rates for the different channels. If the Higgs is the mechanism by which masses are created in the standard model, we can predict these rates. We can see the different values and their statistical errors. The green band is what happens when we fit everything jointly. And you can see that the green band is not too far from 1. There is some indication, not everything lines up exactly, perfectly, but within statistical errors, this is compatible with the standard model within the errors. So what we see is compatible with the expectations for the standard model, but some channels require more data to pin this down precisely. And in fact, the most important thing would be, if we get more precise values and see a deviation, then we're seeing the breakdown of the standard model, which is the true purpose of our exploration, to find new physics processes beyond what we already know. We can also, using these rates for the different channels, measure the couplings of the Higgs, compare how it interacts, how strongly, with the different types of particles, both the quarks and leptons, called fermions, which make up the basic constituents of matter, and the particles called bosons, the photons Z and W, that carry the forces of nature. Again, you see the errors are still pretty big. You see the error bars here, but more or less line up with the standard model prediction of 1, normalized to 1. Where do we go from here? Today we had 2 very nice talks by 2 members of our group, one named Su Xie, who spoke to the PMA Division Chairs Council today and gave a very beautiful talk also on this search for the Higgs, and also some of his current work together with Xie is a Millikan Fellow, Emanuela DeMarco is a Tolman Fellow, and Yi Chen is a very talented graduate student in our group. What they're doing is measuring the quantum properties of the boson. The detailed properties in this channel with 2 Z bosons going to 4 leptons, how the Z bosons are created, how the particles decay, what are all the angular distributions. Part of the issue is to calculate the theory in all its generality, very computationally intensive, along with the experimental investigation once that computation is done about how the data agrees and to which extent, and what is the properties of this particle. What is its spin? What is its symmetry if you change its charge? That is a particular symmetry which changes a particle to an antiparticle. What about its properties on the mirror symmetry called parity? So these are computationally intensive quantitative studies leading to new qualitative knowledge. So now we've finished talking about the Higgs, and before I go on...
Never mind person of the year, what about particle of the year? Meet the Higgs boson. Ever since the Standard Model of Physics was formulated, there's been a piece missing, a particle that would give other particles mass. Unless it could be found, one of the great edifices of physics could come tumbling down. It was in the 1960s that Peter Higgs, an astrophysicist from the University of Edinburgh, first developed the theory of a particle, or a boson, that in effect would give energy mass. It takes very big machinery to find very tiny particles. The Large Hadron Collider that straddles the border between Switzerland and France is a mega machine by any definition. It cost $10 billion to build. Protons were accelerated around a racetrack at speeds coming very, very close to the speed of light, at which point they would collide and produce a shower of smaller evanescent particles and determine if one of them was the elusive Higgs boson. This summer, on one of the earlier runs in the collider's life, the particle was found. The discovery of the Higgs boson was hailed as a monumental achievement for a lot of reasons. First of all, it preserves and confirms the Standard Model, on which half a century of physics has been built. More important, as the boson decays, we could learn more about some of the deeper mysteries of physics.
So much for the Higgs boson, or what may be the Higgs boson. So what lies beyond? It leaves us with so many questions. Even in the presence of a candidate Higgs particle, are there more Higgs particles? What's the nature of dark matter? Is physics in the early universe unified into one basic interaction? Why is gravity so weak compared to the other interactions of nature? Why do neutrinos and quarks oscillate from one type to another as they travel? Why is the universe filled with mostly matter and so little antimatter? Where does the pattern of particle masses and the families come from, and what is dark energy? We know so much, and yet we know so little. Looking at this list of questions, one is inspired by William Blake to ask, what immortal hand or eye could frame thy fearful symmetry? Speaking of the universe. Okay, what about the other 96%? As we know, normal matter is only about 4 or 4.5% of all the energy in the universe. We know that dark matter exists, and what's its relationship to particle physics? We know, since the early observations of Fritz Zwicky here at Caltech in 1933, that there's not enough visible mass in galaxies or galaxy clusters. For spiral galaxies, there's not enough mass without the dark matter to hold them together. If we look out on the large scale, we also see that the images of galaxies is distorted by some matter which is bending the light between the source and where we are, and creates very strange effects visually. Rings, multiple images, and distortions. One can unfold the map of what you see, one can unfold what you see to map the actual dark matter. We actually know also about dark energy, although we have no particle description, that it's not only accelerating the edges of the universe, but also, depending upon the amount of dark energy, it dominates the entire structure of the universe, the ratio of what we see in terms of concentrations of matter and the voids between them. Okay, so dark matter. There is 5 or 6 times more dark matter, we know from these measurements, as compared to normal matter. What could it be? A leading possibility in our minds is a more general theory than the standard model called supersymmetry. For every particle that we know, every fundamental particle, there's a partner. For quarks, there are squarks. For gluons, there are gluinos. For Z's, there are zenos, and so on. Why is it so important? Why is this such a compelling picture? Because in the standard model, when we try to go back to the early universe, it just falls apart. The Higgs mass essentially blows up, and its couplings blow up. And this provides us with the partners a way to moderate that explosion of the theory and have a stable Higgs mass also in the early universe. The interactions of nature come together naturally in supersymmetry without any fine-tuning. It was found starting in 1982. And for most forms of string theory, the one candidate we have of all the fundamental interactions, that this relies upon supersymmetry. Experimentally, if such a model of physics beyond the standard model exists, there are these long decay chains. Here you create a pair of gluinos, they decay to normal particles, quarks, and eventually some leptons. And at the end of the chain, the lightest supersymmetric particles interact very, very weakly with matter and would escape from the detector, leading to dramatic signatures, such as shown here, with multiple jets and missing energy from the energy escaping from the detector. So how to find supersymmetry? Or in general, how to search for dark matter? This is also an area of investigation where Caltech has a leading role and where my colleague, Professor Spyropoulou, has a great expertise and has innovated many of the new methods. So Professor Spyropoulou and Chris Rogan have invented a technique called the razor technique. What you do is, in this picture, here's a simple example. If I create a pair of squarks, they would decay to a quark leading to a jet, and also these weakly interacting particles which escape. And how to find out the mass of this hidden mass scale that results from these new particles being produced. By this new technique called the razor, one can use variables that measure the mass scale, also are sensitive to the missing energy, which is a signature of these events. And you go to a special frame in which the final particles have a fixed momentum relative to the hidden mass scale. And that's the key. And several members of our group have worked on this. This is a very powerful way to separate signs of supersymmetry from many normal background processes from the standard model. And this has turned out to be the most sensitive way to search for supersymmetry. And in the parameter space of the possible variations of supersymmetric theories, it is the most powerful one. Here's an example where the analysis has ruled out a large region, but of course still left a large region still allowed. And as we progress at the LHC in luminosity and energy in the longer term, we'll be able to explore much of the remaining space and find out if supersymmetry is the source of dark matter, and if supersymmetry is that more fundamental theory that lies beyond the standard model. But in these measurements, we've already reached beyond the 1,000 GeV scale, 1,000 times the equivalent energy of the proton of that order for both quarks and gluinos. Okay, another investigation is a search for extra dimensions. This is related to the question, why is gravity so weak? And one of the ideas that's postulated is that we and our standard model particles that compose us live on a sort of membrane in a larger space which has extra dimensions. And only gravity essentially can propagate in the extra dimensions. How can there be extra dimensions? And why don't we sense them? So there's an analogy of an acrobat and an ant. So here's the acrobat, Nick Wallenda, and there's also an ant there somewhere crossing the Niagara. There's Nick Wallenda. Well, it's very clear, as you can see here, that he can only move in one dimension, forward or backward. If we zoom in further, we see the ant, and he can move in additional dimensions. He can move along and also around the rope. And so that's the idea. When you look at things on a small enough scale, equivalently at a high enough energy, you can probe the extra dimensions. So here's the picture. We live on the standard model brane here in a larger space. The Planck brane is where gravity is mostly. And how do we search? We search for new resonances, new particles that could show up through resonances in this space between these two membranes in different channels, E plus, E minus, at very high energies now, and 2 photons. And we've already probed up to the range of 2,000 GeV in mass, searching for such particles. And of course, since you don't see it in the newspapers, we didn't find any. The occurrence of a Higgs boson at 125 GeV is also remarkable in other ways. Thinking about supersymmetry, such a mass is pretty heavy, and it's hard to fit in the simplest forms of supersymmetry. So what? We know that nature tends to be more subtle and perhaps at least a little smarter than we are. So supersymmetry may not be so simple. And seeing this Higgs mass has actually spawned an industry this summer exploring exotic extensions, not only of the standard model, but of the simplest forms of SUSY, of supersymmetry. Another exotic thing is 125 GeV puts us in a very strange place in our universe. The Higgs field, which fills all of the universe, defines our vacuum. But the Higgs is not heavy enough to maintain that vacuum for a time equivalent or longer to the age of the universe. So maybe that vacuum that we live in can suddenly disappear. It can actually tunnel to another state. And so here's the region in terms of the Higgs mass versus the top quark mass, which is calculated rather precisely in the last few months. This is the stable region, this is the unstable region, and here we are in the middle, metastable. It means that, well, the vacuum may be unstable, but we don't have to worry too much because it lives for a long time. Well, we don't believe that because we're here, and we came from the early universe when the energy was extremely high. So what we do believe is it's probably a sign of some new physics that lies between us and the Big Bang. It's somewhere in the middle, and we have no idea what it is. And this is an amazing thing to learn just from that one fact, the mass of the Higgs particle. Okay, so I'd like to conclude with a number of expressions in the midst of this enormous enterprise, which is the CMS experiment, the LHC program. What is the role of Caltech? As Tom said, we have multiple leading roles in the physics, in the conception of the detector, in the way in which the detector is triggered, selecting which events, which data is recorded for further examination, and in many aspects. Our group focuses on discovery across a broad front, not only the Higgs, but supersymmetry or alternatives, other exotic forms of new physics. And this is an expression from my colleague Maria Sporopoulou: explore the full landscape, determine which new physics, find out whether what you see is conventional things such as the standard model Higgs or something which is more exotic and imposter. To have this role, we have world expertise in a number of areas, new methods of precise calibration you saw, development of unique global system technologies, innovative and ambitious analysis methods, and new statistical techniques, in-depth understanding of the detectors, the computing, and state-of-the-art data networks. Our students are really the source of all this wealth. We've had some fantastic, talented students. In 2011, there are 7 CMS awards for work on the detector. CMS is an enormous enterprise with 170 institutions. In 2011, for work on the detector, on the electromagnetic calorimeter, the crystals, and to calibrate them precisely on the trigger, and also on the hadron calorimeter, and suppressing the noise to make its performance much higher. 3 of the 7 student awards went to our group at Caltech, among 170 institutions. Actually, if you think about the statistics, is that random? That's 5 sigma. It's not random. As important, this is the fact that at Caltech, undergraduates are a fantastic and I think a unique resource. As Tom said, we've had the privilege of mentoring 90 such undergraduates throughout my career, and since the arrival of Professor Spyropoulou, this has only increased, and I think that's great. So this is 4 of our 7 SURF students, Alex, Lisa, Valère, and Max, with very different and very powerful talents, actually, we found. This is not the CMS detector. This is a photograph. So we were having a party, and they made this enormous photograph on the surface. Just think what it was like for these summer students to arrive at CERN during the summer. You know, this project had been built for many years, and we were taking data, and to have a discovery. What could be greater? Okay. So we've had very many visitors. Here's June 9th, 2009. There's one well-known visitor, Bill Gates. But the more important distinguished visitor is Jean-Louis Chameau, who arrived a few days later, with members of our group and some of the physicists and engineers who were there at the time. And we also had a very nice visit recently from Ed Stone in November, who visited with our group. You see Ed there with Maria and some of the students and postdoctoral fellows in our group. And here you see Ed visiting the assembly hall for the magnets, where one of the leaders of the LHC team is explaining how the magnets are constructed and how they were tested. And here's Ed in the CMS control room giving permission to the LHC to inject the beams. People at CERN trust people from Caltech. Okay, so this was a picture which I showed in my last Watson lecture of CMS, this wonderful modular detector about to be closed in 2009, just before physics, right after the time of Jean-Louis' last visit. And we're also looking forward to a very nice, another visit from Jean-Louis and some of you in the audience, some of our distinguished visitors who will be visiting us this coming May. What about the long-term future? This is a log scale of this so-called luminosity. Down here is a start. And I had to add these arrows to the previous graph to show that we actually did better in the early years than was originally thought. But we're just beginning. We have 29 inverse femtobarns, 2 quadrillion collisions. But what will happen in the coming years is, well, as Tom mentioned, we're going to have a shutdown to upgrade the accelerator so we can reach the full energy. Also, the number of bunches will be doubled. The tests show we can already do that. That's very promising. It will take nearly 2 years. Then we'll go up to, in luminosity, to 500 inverse femtobarns, about more than 15 times what we have now. Then there'll be an upgrade of the injector. Along the way, during these long shutdowns, the detector will also be upgraded, a new tracker, and eventually in later years, also new calorimeters. So here, around 2022, we'll begin another phase called the high luminosity LHC. And to reach 3,000 inverse femtobarns, or 100 times the data we have now, 100 times the reach, but even more than that, because we'll be at higher energy. And then beyond that, starting around 2035, this is now we're really talking about the next generation, a high energy LHC using the new high temperature superconductors used in tandem with conventional superconductors to make magnets of 20 Tesla or 200,000 Gauss, providing an energy of 33 TeV compared to the design energy of the LHC of 14. So we will continue to extend our reach. And we're confident that somewhere along this very long program, we will have more discoveries and our thoughts about physics will change. Preparing for the high luminosity LHC, I just want to say one thing in closing. There is detector research and development going on. Our crystal laboratory is working with this new crystal called LYSO, lutetium yttrium orthosilicate, a fast, bright scintillator, very radiation hard, and also studying radiation hardness issues of the photodetectors and the optical fibers in this design. And also Professor Sparapoulou is working on solid-state photomultipliers for very high precision timing to sort out the particles that come from the interactions point in this very dense environment from all the extra interactions which accompany the interaction of interest. So that's it. This is our journey to discovery. The LHC and CMS have performed magnificently throughout this 3-year run, which is now just completed. We've discovered a new heavy boson at a mass near 125 GeV. It's generally compatible with the standard model boson, but the study of whether it really is that boson of the standard model is underway. Measuring its decays more precisely, looking at trying to measure its spin and its symmetries with much more data than at the time of the announcement in July. So one way or the other, we will soon have more to say on whether it is the Higgs boson of the standard model. But we know there is some theory which is more fundamental beyond the standard model. The search for this theory has just begun, and Caltech is leading the way. And beyond that, it will take another generation of physicists, now maybe we're talking 2 generations, to figure out what the heck is dark energy. So this was very fast. And so further information for you, I can recommend a book by our own Sean Carroll, The Particle at the End of the Universe, another book, Higgs Discovery by Lisa Randall, and some other sources you can find on the web. As Tom mentioned, this is Science Magazine Breakthrough of the Year, and so there are beautiful articles in the December 21st issue of Science Magazine to explain to a wider audience, to a wider scientific audience, what this was all about. And finally, for those scientists and physicists, you can actually find beautiful articles on the discovery itself. And so that's my lecture. I hope you enjoyed it.